Questions? Please don't let these things go. If they don't go well, come and see me. Let me do 3. Find the x-intercept of the graph. That's a good question. Okay, here's what I would do. I would start with this. Yes, that's the regular graph, correct? What does this tell you to do? Yes, we had to plug in a -1, didn't we? So it's going to move over left 1, which means that the x-intercept is -1. Okay? All right, let's do this. Graph the linear system and check the solution. So you're going to graph it. You're going to check the solution. When you graph it, you're looking for an intersection point. That would be the solution. So you have choices. You can change it into y equals mx plus b, which you might want to do because you're going to get a decimal. But you could also do this. So if I plug in 0 for x, what's my y going to be? 5, positive 5, right? Divide both sides by -2. Okay. And then if I plug in 0 for y, what's my x going to be? -2. Okay, I'm going to plot that first one. Over 0, up 5. And -2, 0. This is the hard part. You got to really draw straight lines for this, or you can't always find the intersection point on the graph. So you got to make sure you draw a straight line. And then if you do this one, x, y, 0 for x, 0 for y, what do you get for y when you plug in 0 for x? -3. And if I plug in 0 for y, I'm going to get 6. So over 0, down 3. 6. Okay. Now you got to find the intersection point, which is right here. And it should be 1, 2, 3, 4, -4, -5. That is the solution. Check the solution. That means you plug it back in. I'm not going to make you do that, but how could you check to see if it actually truly is the solution for these? Plug it into both of them. Okay, now let's stop. Go up here. Let's see if we can label these by these words. Is this a consistent or an inconsistent system? Consistent because it has one solution. Is it independent or dependent? Independent. I can spell. Consistent and independent. Okay, it has a solution, at least one, and it's independent because it has one. Okay? Okay, flip it over. Okay, I'm going to show you something nifty on the calculator because I feel like it's far more accurate on the calculator. And as long as you know how to do it by hand, I don't care if you do it on the calculator. Yes, so do you have a graphing calculator? Grab one if you don't. Okay, you have line 1 and line 2 here. I'm going to write line 1 in y equals mx plus b form. All right. So I just took and I wrote both the equations in y equals mx plus b. So write those down. Do y'all know how to do this on the calculator? Some of you might already. It's a beautiful thing. Okay, what we're going to do is we're going to put both these equations on the calculator. Now, you have fractions. Make sure all this stuff is cleared. No plot is highlighted and everything else is cleared. You have fractions, so you're going to, I always put my fractions in parentheses just to be safe. -3/2 x minus 2. And then go down and put the second one in. -1 divided by 3 x plus 1 divided by 3 in parentheses. Are you there? I just put those two equations on. Yeah, they're both negative. That's okay. All right, so we all have the same window. Push zoom 6. Zoom 6. We all have the same window. Yeah, yeah? All right. I want the calculator to calculate something off this graph. So these are kind of the graph buttons here. Where do you think I would go?
Calculate.
Calculate. I want the calculator to calculate something off my graph. These are the graph buttons. So I'm going to go to calculate right here. Okay? So go second, calculate. Oh, look at that. Would you look at that? What's number 5? Number 5 is intersect. So push enter. Oh, no, that's not what I wanted. Sorry. I want number 5. Yep. Okay. Now it kind of asks you something funny. It says first curve. Well, these aren't curves, but it's just what the calculator's got on there. It needs you to tell it the two different lines that you're looking for the intersection point. So it's blinking right here on this cursor, and it's saying, is this one of your lines, first line? And I say, yeah, that's one of my lines. So I push enter. And then it jumps up to the other line, and it's saying, is this the second line of the two lines that you're looking for the intersection point? And I say, yes. That is my second line, my second curve. And then it's saying, do you want me to guess the intersection point? And I say yes. Yes, and there it is. Look at that. -2, 1 is the intersection point. Isn't that beautiful? Well, you can kind of graph it yourself. Once you have it in this right here, all you got to do is do -2, down 3, over 2. There's your first line, yes. I just graphed line number 1 using the y-intercept and the slope. Graph line number 2, it's about 1/3 here, down 1, over 3, about here. And you should end up with an intersection point about like that. -2, 1. Beauteous, huh? Okay. It's dependent because there's infinitely many solutions. There's tons and tons of points where it overlaps here. Okay? All right. Let's do this one. If I move this around, I'm just going to tell you what it is. This is equation 1, equation 2. Equation 1 moved around would be y equals 4x plus 5, if I put it into y equals mx plus b. Equation 2 would be y equals 4x minus 2, if I put it into y equals mx plus b. What do we notice about those? They're parallel. I noticed that because they're the same slope. Same slope, different y-intercepts means they're parallel. Parallel lines ever intersect?
No.
No. So, is that going to be consistent?
No.
It is not consistent because it does not have at least one solution. It's inconsistent. No solutions ever. Okay. 2 is already in y equals mx plus b, isn't it? Okay. So I'm going to put 1 into y equals mx plus b. It's 2x plus 5. Now I'm working with these two. If I were to graph those, let me just sketch them real quick. You could throw them on the calculator if you wanted to. This first one starts at 2, goes down 1 over 1, so it's going to be something like that. The second one starts up here at 5, up 2 over 1. It's going to be something like this. And here's my intersection point. -1, 3. Okay? If I were to get that on the calculator, that's what I would get. It's got one solution, so is it consistent or inconsistent? Consistent, and what? Exactly one would be dependent or independent? Independent. All right, right on. Okay, a soccer league offers 2 options for membership plans. 2 options. Option A includes an initial fee of $40 and costs $5 for each game. Option B costs $10 for each game played. There's no initial fee. After how many games will the total cost of the 2 options be the same? So I'm going to write my equation A. How much does it cost for equation A?
40.
40 plus 5x, right? And option B does not have an initial cost. It just has a how much per game. 10x, correct? Okay. This is kind of a pain to graph. Yeah, I'm just going to sketch it. You don't really have to. It looks kind of like this. If you go up by 5s, 10, 15, you're going to end up here at like 40. So it's kind of like this. And this just kind of comes up like this. It's a little steeper. It's kind of a yucky graph. Let's not even think about the graph. We would actually be looking for the intersection point when they're equal, but we could also do it algebraically. Look at here. I want to know when A is equal to B, correct? I want to know when they cost the same. So I could just write, well, I'm going to set A equal to B. And I'm going to say, okay, I want to know when 40 plus 5x equals 10x. That's what I want to know. And if I solve it, subtract 5x, subtract 5x, 40 equals 5x, and x equals 8. At 8 games is when they're equal. Could you whip that on your calculator?
I just did.
Yes. And you can get the intersection point off your calculator. Sometimes you have to adjust your window. You guys, would this show up on a regular viewing window? No, you have to make your X max really high, okay? So you sometimes have to adjust the window.